We'll quote you on that. You know that. We'll just put this clip. We'll just put this clip live. In mathematics, you don't need to know anything. You don't need to do anything. By Lena Voita. Just this clip. It's gonna be.
I think it's the do bit. You don't need to do anything.
And the funny part is that it fails sometimes, so it just chases you randomly.
Right. Well, I guess we'll have to code it up at the weekend.
Hello folks and welcome back to the channel. Today we're going to be talking with Lena Voita, but before then I wanted to spend about 10 minutes or so just talking about some of the confusion I think that I've noticed arising from the Kenneth Stanley episode. So if this is interesting to you then please watch it, otherwise you can skip forward on the table of contents to Lena Voita. Now I wanted to clear up a few things, right? The first thing is, I think if you take one thing from that episode with Kenneth Stanley or his ideas, that one thing should be the concept of deception. And deception is when your objectives or stepping stones, they lead you in the wrong direction, right? Assuming that your goal, which is also a stepping stone, is even the right direction to be going in the first place. But it's a really important concept that any search problem has deception, which means we cannot trust the gradients of the stepping stones. Even reinforcement learning algorithms, they acknowledge this with reward shaping. Reward shaping is about creating intermediate stepping stones where you can trust the gradient. So any ambitious objective has deception. That's really important. Now, any goal that requires knowledge that we don't yet have, and by the way, knowledge is the same as a stepping stone. For example, how do we build artificial general intelligence? Or how do I become a millionaire or a billionaire? These are deceptive goals, which means we cannot trust the gradient of the stepping stone, right? There's a false compass. As discussed on the show, some goals are surprisingly undeceptive, like landing on the moon or building rockets or building a bridge or some software engineering projects. And this is because we already understand what all of the intermediate stepping stones are. Now, in the case of landing on the moon, actually, some folks in China about 3,000 years ago discovered the key stepping stones to make that problem happen. So now we can monotonically increase on the knowledge that we already have, and we know we can get to the moon. It's a different story of artificial general intelligence. If we monotonically increase on GPT-3, it's a false compass. It will not lead to artificial general intelligence. Almost everything that happens in the work environment at the moment works on the principle that we should exploit what is already known and not waste precious time with deviations and people self-ideating and innovating. I see this a lot, right? Because I've managed teams of data scientists and machine learning folks, and all they want to do is build their resumes and experiment with things and be researchers and so on. And, I can completely understand why a lot of the senior leadership in large corporations do not want that to happen. Right? It's horrifying because you think, my God, people are wasting time and money on things which are taking away my predictability. So there's a huge kind of dichotomy between science and engineering. Science is about exploration and engineering is about exploitation. And you can argue that in most businesses, the focus is on exploitation. So if you do any MBA course in business, the first thing they tell you is it's all about predictability. It's about reducing surprise, it's about convergence, and it's about increasing velocity. That's what you learn on an MBA course, right? So to be a good stakeholder even, that I was on a presentation about this the other day, the key there that I was told is that to be a good stakeholder, you have to be predictable. You have to be obedient. You have to treat other stakeholders like black boxes. You have to give them the information that you want. You have to learn their behavior, a bit like you would a machine learning algorithm, and then you have to be able to predict what the output is. So give them the answer that you want to give them, and then you can predict the output. It's a similar thing when you have direct reports. You want them to be as predictable as possible. It's no coincidence that in the corporate world, there is a certain behavior that emerges of obedience and consistency. And it's all about scale, because to do things fast in a large scale organization with, role fragmentation, multidisciplinary teams, you need predictability. And that's why you have a certain type of people in these institutions. So, if you want to scale yourself in a large corporate, what do? You make yourself transparent and you be as predictable as possible, right? So there's a test. What would Tim do? If people can answer what Tim would do, it's a good test that you can scale yourself. If I know what my reports do, it's a good test that I can delegate to them and I don't need to be in the meeting anymore because I can trust that they're going to do the right thing. Okay, so none of this should come as a surprise, but for good or bad, it's the opposite of stepping stone collection, right? This is all about velocity. It's about exploitation. It's the opposite of innovation. Innovation is about surprise. A lot of MBA folks will tell you that they're creating an innovative culture. They're not. They're doing the complete opposite. They're creating an agile, high velocity culture. There's a difference. So when you read Kenneth's book, and Keith said that he was making quite a hyperbolic argument, like a black and white argument, but I don't agree. I think the most important thing that Kenneth was pointing out in his Greatness Cannot Be Planned book is that there is a tyranny of objectives. Now, it's not hyperbolic if you understand what he meant. So in science and institutions and the business world right now, even in education, there is no divergence. And the reason for that is the objectives are fixed. So we get teachers to monotonically improve on grades, right? So that is a convergent behavior. Divergence is all about discovering new problems, right? It's about problems, it's not about solutions. So what should be clear is that if you fix the objectives, you can't be discovering new problems. Actually, it blinds you to the discovery of new problems. That's the really key concept. So yes, it's certainly true that there is some exploration out there because there are some people in their garages following their own gradient of interest without receiving any money from the government or anything like that. But I think what Kenneth is saying is that as a society, we are not discovering new problems because we are so focused on solutions. What he's saying is that the government and large institutions should pour huge amounts of money into discovering new problems, because the ironic thing, or the paradox, is that it's only by looking for new problems that we will discover better solutions to the problems that we already have. That's it. Right, so the other misconception is that people think Kenneth is arguing that we should abandon objectives and not use objectives. That's not true. Okay, so in some of Kenneth's early work on quality diversity, he was making that argument. We should still use objectives, but use a different type of objective. Use an objective which has a kind of behavioral characterization or entropy, which we can increase monotonically, which means we can trust it better as an objective because it's less deceptive. So basically, all of the early work in quality diversity was about creating objectives that had a better gradient, which had less deception. Okay? What he's saying now is that we should flip the script. We should focus on problems, not solutions. We should focus on having as many objectives as possible, because a system that has a panoply of objectives has no objective at all. That's the key thing. Just like evolution, we have a panoply or a cacophony of niches, people following their own niches and their own gradient of interest. That's what he thinks we should do now. And in the context of machine learning, he's advocating for meta-learning. He's saying we should meta-learn new objectives. People have asked, does PickBreeder have an objective? Well, again, it's the same thing, right? Every single person in PickBreeder is allowed to follow his or her gradient of interest to its logical conclusion. It's certainly true that the gradients will be collinear in some sense because they're all going to be earthly gradients. There is a divergence to it because people won't recognize the images, but when the images become heliocentric or earthly, then it'll become a convergent behavior. So we'll talk about PickBreeder in a minute. Now, deception is the single most important concept. If you take nothing else away from the Kenneth Stanley video, please let it be deception, right? Once you clearly understand this problem, you will question gradient-based methods for the rest of your life, I can assure you. You just can't unknow this information. It's a little bit like when Walid Sabah came on the show and was saying about GPT-3, it doesn't understand when you say a corner table wants a beer. It doesn't understand that the corner table is a person, because there's this problem, the missing information problem, right, in data-driven statistical machine learning methods. The information is not in the data. And once you know this key concept, you recognize the problem everywhere. It's like a sore thumb. It sticks out at you. And it's the same thing with deception. Once you recognize this problem, you'll see it everywhere. You'll see it everywhere. It's a huge problem. So yeah, basically you will know where the landmines are now once you understand this concept of deception. So coming back to PickBreeder, why don't we look at a phylogeny? Now this is one of the pictures that Kenneth himself bred, and it looks like a pig, or it looks like some kind of animal. And if we trace all of its ancestry all the way to the beginning, the key concept here is deception in a search space. So what Kenneth is pointing out is that the intermediate stepping stones look nothing like the end result. So this was truly a divergent process at the beginning. This was just individual people following their own path of gradient of interestingness. And it's only when it got to this generation where suddenly it became something that was quite earthly or heliocentric. So this point of the phylogeny was divergence, and this point is convergence. And it's really important that we make this distinction. Now, let's use the example of rocketry, right? So the Chinese, a few thousand years ago, were experimenting with all sorts of random things with fire and water and goodness knows what else. I think there's something here called a surface running torpedo. And it's only when they got, at some point in the lineage here, that it started to resemble conceptually what a rocket is. So once you get to the key stepping stone where you can now converge, or you can trust the gradient of monotonic optimization, then it becomes an engineering problem. So this is what they did in the 1960s. They put a man on the moon. So they had all the knowledge, they knew what the stepping stones were, and they could use a gradient-based optimization, and they could get a man on the moon. This is basically what we do in the work environment at the moment. We know what the stepping stones are, and we are ruthlessly improving the velocity of the process because it's an engineering problem. Right? I personally believe that GPT-3 is here. So GPT-3 is at a stage where we have a stepping stone, we have an objective, but it's a deceptive objective. So if we optimize on this gradient, we're going to go in the wrong direction. Artificial general intelligence is down here, we're going to be going in the wrong direction. Now, another key concept is Pick Breeder a good analogy for real life? Because a lot of the argumentation here hinges on that principle. I strongly believe it is, right? And that is because we know for sure that many ambitious search problems, even in computer games, for example, they have deception. Of course they have deception. So if deception exists, and if gradients have a false compass, then why are we using gradient-based methods to find good solutions to these problems? It's completely balmy. Now, I wanted to give another example here. So this is the famous skull in Pick Breeder, and as Kenneth was saying, right, that the early stepping stones do not resemble the skull. So if we trace it all the way back to the beginning, as you can see, it's just a kind of pattern. It's just a weird gradient pattern. And the way NEAT works is that it hinges on this principle that Kenneth has observed in evolution, which is that there's a monotonically increasing arrow of complexity. And that's why the topology of the underlying CPPN, the convolutional pattern producing network, is increasing in complexity. So when we look at the phylogeny here, we have some stepping stones that look nothing like a skull, and all of a sudden we have something that looks very anthropomorphic on the fourth stepping stone. And at that point it becomes a convergent process. So you can see in Pick Breeder that loads of people now kind of branch from this anthropomorphic image and create lots and lots of interesting children. So at this point it becomes a convergent process, but at this point it was a divergent process. And the irony is, if you tried to find an anthropomorphic image directly, you probably wouldn't find it. You're more likely to find it by accident, by following your own niche or your own gradient of interestingness. That's the key thing with Pick Breeder. Now, it's interesting to have a quick look at this as well. So as I was saying on the previous episode, a pattern producing network. So it's just a neural network that takes in a spatial input and gives you an RGB output. And you might be interested to know, well, what was the topology of that network for this skull pattern? Well, this is it. This is the skull generating pattern producing network. And it's absolutely fascinating, right? I mean, I think that the color tells you what the weight of the connection was, and then these things here are different activation functions and different neurons. And as you can see, this then produces the skull pattern. And this was learned through a combination of the NEAT algorithm being human augmented by folks following their own gradient of interest. Absolutely fascinating. So the other thing I wanted to do is take you folks on a bit of a tour de France of some of the approaches for doing novelty search and the lineage of those approaches. Now, in the show, we were quoting this paper, actually, Abandoning Objectives, Evolution Through the Search for Novelty Alone. And this was one of the seminal early bits of work in quality diversity and novelty search. So I think when Kenneth wrote his book, Greatness Can't Be Planned, he was probably thinking along these lines. That was what he had in his head. Now, in the paper, they have an example of a hard maze which has deception, and they give an example of what a genetic algorithm using NEAT with the distance function as the goal to the reward would look like. But I'm going to fill in the gaps here. So what I've done is I've imagined what would it look like if you had a hard maze, which was a reinforcement learning algorithm with epsilon greedy. Now, the whole point here is that search problems have deception. So if you have the wrong objective, which has deception, which is to say you can't trust the gradient of optimization optimization, it means that you're going to get stuck in some kind of local minima. So I'm imagining that if you had a reinforcement learning agent and you trained it on lots of different episodes, probably the coverage along the map would not look very good. It would look something like this. Okay, so the objective here is fixed, and this is why we have reward shaping in reinforcement learning, because we can't trust the gradient of the objective. We have to create stepping stones manually where we can optimize on the subgradients of those stepping stones. Now, the next thing he did was this is what he showed in the paper. So he said, well, what if we have a genetic algorithm using NEAT with the distance to the goal as a reward? Now, a genetic algorithm, it's all about the diversity. It's a population-based method. So being able to cross over diverse instances, it actually gives you better coverage around the map, right? So still one goal, which is the distance to the objective, but we are introducing this concept of diversity preservation and crossover. The next thing that Kenneth showed, and this is the key idea with novelty search, is what if we do not optimize at all on the distance to the goal? Right? And personally, I would argue that it's cheating, because in many situations it's a partially observable problem and you don't actually know what the distance to the goal is. So, there's an argument to do this anyway. But what we do here is that it's still a genetic algorithm. It still has one objective, but we design the objective in a very clever way. We use a behavioral characterization, right? So the objective now is map coverage. Right, and the really clever thing about using this behavioral characterization, which is kind of like entropy or map coverage, is it means that you can monotonically increase it. So if you monotonically increase it, you trust the gradient, and it means that a gradient-based method will actually give you better map coverage. So that this is not abandoning objectives. This is basically designing better objectives. But the irony here is that it's a better designed objective, so you could still use a gradient-based method. All he's doing is he's designing an objective that has a gradient which is trustworthy. The other thing I wanted to talk about with genetic algorithms in general is that they are convergent, right? So you might think by having diversity preservation and by having a kind of entropic behavioral characterization that you would overcome this convergent behavior. But you don't, right? It's still convergent, and the reason it's convergent eventually is you have a fixed objective, right? So if even this genetic algorithm with NEAT using the behavioral entropy as a fitness function, if you look at the convergent behavior, it will still converge. It's still an asymptote. This is why we need to move towards meta-learning the problems, looking at the problems as well as the solutions. Because if the problem is fixed, a problem is the same thing as a stepping stone, right? So if you're imputing the knowledge of what the stepping stone is into the algorithm, then by definition, it's going to be subject to deception. You need to be learning new problems. So the other thing is, before we get to POET, Stanley has been doing some other work. So you may have heard of this Go Explore, which is kind of like an evolution of the behavioral characterization problem. So I would say that this is still an incremental step of quality diversity, and it's overcoming two of the major problems that they saw with quality diversity algorithms, which is namely detachment and derailment. So on this detachment example, they show what that looks like. So you might have an intrinsic reward that's distributed throughout the environment, and then an algorithm might start by exploring the purple, a nearby area with an intrinsic reward, and then by chance it might explore another equally profitable area, and then exploration fails to rediscover the promising area that it's detached from. So you get detached in this region because it had no novelty. So the idea there is to almost start from a region that was discovered before, just to get around the detachment problem. The other problem they talk about is derailment, which is where there's no mixability between nodes in the phylogenetic tree, which means that the agent was derailed from returning to the state that it's once in. So I see this as very, very incremental, really. So in my opinion, all of this is still old hat. This is not interesting. The really interesting thing that's happened is with POET. Now, POET was released by Uber. Stanley was working for Uber a few years ago, and this is where things really got interesting. So in POET, you have a meta-objective, and you learn objectives through meta-learning. So in POET, you have these agents and you have environments, and the environments kind of monotonically increase, and you swap the agents over. So all of the environments are basically the same thing as problems. Right. So the idea is that you're focusing on problems, not just solutions, and you're meta-learning a curriculum. So there's a really good image here showing a curriculum that was learned as part of POET. And I showed in the video last week an example that Jeff Clune talked about where there was a really complex environment, and in order to overcome the deception of that environment, we needed to kind of cross over with one of the simpler environments and then come back again. So the idea here is that we are learning a curriculum, but the curriculum is so weird that we wouldn't have been able to come up with it ourselves. Remember, in order to do things like artificial general intelligence or to solve complex problems, we do not know what the stepping stones are. We have to learn the stepping stones, or we have to discover the stepping stones. And this is precisely what Poet is doing. It's a stepping stone collector, right? Now, the other fascinating thing that I thought about is, why don't they use something like Poet for language modeling? So you could have a meta objective, which is your perplexity, and then you could have some kind of increasing curriculum of tasks, which could be meta learned. And that may well overcome the deception in the world of language modeling, right? Why don't they do that? Maybe they will do that, I don't know. And I also said in the show that this is very similar to Francois Chollet's conception with the ARC challenge. Well, the whole idea of Francois Chollet's neural program search conception is that, first of all, it's a search problem, and secondly, you are meta-learning to solve problems that you don't know about, right? I think he called it developer-aware generalization. So actually, Francois Chollet and Kenneth Stanley, they're going in the same direction. We need to be thinking about learning problems that we are not yet aware of in order to solve problems that we are aware of now. Okay, fantastic. Anyway, I really hope that clears up some of the confusion, or maybe it's just created more confusion, I don't know. But let's move on to Lena Voita. Thank you very much.
Hi there. Welcome to this conversation with Lena Voita. As you know, we at Machine Learning Street Talk are always extremely excited to talk to new guests and guests from different fields. And sometimes we get a bit too excited. So this time we actually forgot to press record for the first 10-15 minutes for this conversation.
I'm so sorry about this record button. Oh.
Yep, it's our bad as well. Now, fortunately, we caught it in time. We need to build, like, this could be a fun machine learning project, so Tim, in your chair, we'll build like a taser. Do you know Michael Reeves from YouTube? You should watch Michael Reeves. He's like an engineer. So he does a lot of stuff with tasers. So we'll build a taser into your chair. And then whenever like we have a machine learning model that detects when like the conversation starts, when you do like the intro, like, oh, we have a guest here. And when the record is not active on Zencastr, it just tases you. It's just like, So I'm now the sort of pre-scriptum clown that is supposed to tell what went on during these first 10 minutes. We were just introducing the basic notions of how language models can fail, specifically machine translation models and in general sec-to-sec models. So in a sec-to-sec model, and let's take the example of machine translation, you do usually have some kind of an input sentence in one language, and then you have some kind of an output sentence in another language. Now, initially, you have none of the output sentence, but you are building the output sentence, usually token by token. You can do this in an autoregressive manner in that you predict the first token, and then you feed the input sentence plus the first token again into the system to predict the second token, and then you take that and predict the third token, and so on. This has been giving very good results. However, there is a problem with it. What you do when you train these systems is that you have the source and the target sentence readily available. So you can always feed in not the token you yourself predicted, but you can actually feed in the true token of the target sentence. And that is called teacher forcing. Now, teacher forcing is very attractive, not only because you train your model with actual good data, but also because the samples, if you do it like this, are independent, meaning you can parallelize it. You don't have to do weird loops during your training and so on. However, at training time, you do have the target sentence and you feed in the correct token every step. At test time, you feed in the token that you yourself predicted. So there's a mismatch there between the training inputs and the testing inputs. So just to give an example, if you translate the German sentence, die Katze isst, like eats, it means the cat eats. If you go about and predict the first token, you input the German sentence, plus nothing. And the system might predict the. And then you input the German sentence plus the word the, and the system predicts the second token. Now, the correct token would be cat, but let's say your system is confused and outputs dog. So during training, you know that there should be cat. So your best option is to feed in the word cat again. During testing, you don't have this. You output dog, so you feed in dog again. And you can quickly see that if your model makes some mistakes, then it sort of builds up on these mistakes. And the input of the model gets further and further away from what it has seen during training. So we discussed different failure modes of these models. If you think about what a model like this has to do, it has to do two very different things. First of all, it has to translate the source sentence. So that means that the tokens that it outputs must somehow be the tokens in the source sentence, but just in the different language. So if there is a token Katze in German, there should be a cat somewhere in the English sentence. However, the second objective is to make the output sentence as grammatically correct as possible in the target language. So a very easy approach would simply be to translate each token from language A to language B, but that would be a horrible translation, not because the information isn't there, but because it's grammatically incorrect. So there are these two conflicting objectives, and it can be that during testing, one can just sort of overpower the other, and that leads to failure modes. If the translation information objective wins out, you're going to see really horrible translations, but that contain sort of all the information of the source sentence. These models, even they tend to repeat themselves simply because, so they go like cat, 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 just because that's very probable given the source sentence. And it doesn't really look at what it's produced so far in the output, so it doesn't care about grammar. The other failure mode is the opposite, when it doesn't know anymore how to translate the source sentence, so it says like, well, I'm screwed here, I might as well just, give you a grammatically correct sentence in the target language, a hallucination, a hallucination, a hallucination. At least I'll get some low loss that way. And so it will continue, it will sort of start the output sentence, and then it will continue completely disconnected from what it should translate, as long as the sentence is grammatical, because that is still a low loss output. So if it can't satisfy the two objectives, it will prefer one over the other, and that will sort of give rise to these different failure modes of the model. So that was what we introduced in these first few minutes, and we are of course very sorry that we lost that footage, and we are extra careful and checklisty in the future, which probably means that it will for sure happen again because I just jinxed it. All right, I hope you have fun. See ya.
Yeah, so I did run a little competition on our Discord server. I was curious if any one of our esteemed members could understand what the hell Yannic was talking about just based on these screenshots. And we had some interesting contenders, actually. So Skycore says, no kitten stepping on the White House. I thought that was quite intriguing, actually. An adroit suggestion. Xmaster96 says, I'm so confused right now. Well, it is quite confusing, I'll grant. Henry the meme guy says, has he finally overdosed on amphetamines, caffeine, and lost his mind? Well, we all know that's why he wears the glasses now, don't we? Al B-Bag says, please don't let the cuds die. He didn't, honestly. Yannic's really good about stuff like that. Anyway, I suppose the show must go on.
Hello, Lena. Lena, your blog is incredible. Lots of visualizations and animations. I think it really makes it digestible for people to understand. So yeah, it's great that you've done that.
Thank you.
Do you know Valia Fedorova?
Yes.
Yeah, I met her at ICML probably about nearly 2 years ago now. But it's cool that you know her. Oh, very cool.
She's really nice. Yeah.
Okay, so this is a quick detour. This is Lena's blog, lena-voita.github.io. It's absolutely incredible. So on here, she has all of her publications, of course, but she also has this blog. And this blog is absolutely beautiful. She uses visualizations and graphics in a way that you don't often see, actually. It reminds me a bit of Robert Lange, who we had on the podcast. So let's have a look at some of these articles. So the most recent one is Source and Target Contributions to Neural Machine Translation Predictions. Okay, so we'll go through. Of course, she's written a paper on this as well, but her blog makes it so much more easy to understand. So in this, she's talking about what Yannic was saying before, right? So models hallucinate. As you can see, there's a kind of continuum of influence between the source, so what goes in, and the target, what came out. Because as you rely on predicted tokens in the prefix, then the model has a tendency to hallucinate. So she talks about this dichotomy between the source and the prefix. And she says that models suffering from exposure bias are more prone to over-relying on the target history and hallucinating. So that's, exposure bias is something that increases as you have more and more prefix tokens that were previously predicted, and you're not using teacher forcing, as Yannic was talking about before. Okay, so models trained with more data rely on the source more confidently, and the training process is non-monotonic. It actually has some distinct stages, which is quite interesting. So she says, well, what influences the source or the target? She said that we may expect that some tokens are predicted based on mostly source information, so informative tokens, while others are based on mainly target history, so determiners, but how do we know which information was used? And her TLDR here is that models often fail to properly use these two kinds of information. And this is illuminated in some papers on this matter. So if you look at the attention weights on some of these transformers models, some of these models are only paying attention to punctuation or the EOS token, which means clearly they're not actually paying attention to anything in the input. So they must be hallucinating, which is interesting. Now, how do you reason about the contribution from the source? So there's this thing called layer-wise relevance propagation. Now, I didn't realize this, but it's very similar to one of the original attribution methods in computer vision. Do you remember GradCam, where you have an image going in and you want to kind of figure out, well, which input pixels were most responsible for creating a given prediction? And it turns out that you can do this in pretty much any model, and that's what Lena is advocating that we do in these transformers models. So then, of course, we can figure out which input tokens were most responsible for a particular prefix. So she points out that it's unclear how to use a layer-wise method to something which isn't completely layered, because an encoder-decoder architecture is of course different to these traditional CNN type models, but she asserts that the total relevance is still propagated through the decoder, and the relevance leaked to the encoder is propagated through the encoder layers, and she kind of demonstrates that with this animation here. In her paper, she talks about how to extend this LRP method to the transformer. But anyway, let's do some experiments. So she looked at the total contribution and entropy of contributions, right? So the total contribution is the contribution of the source, which is 1 minus the contribution of the prefix. And she also looked at the entropy of the contributions, which tells us how focused the contributions are, whether the model is confident in the choice of the relevant tokens, or whether it spreads its relevance across the entire input. Now, the other thing she points out is she's interested in general patterns. She doesn't want to focus on kind of micro patterns, so she averages over the entire data set. Now, this is really interesting. So when she does this, she notices that there's a general pattern. So as the target or the prefix token number increases, the model increasingly hallucinates because it's paying less and less attention to the source. And this graph here demonstrates that quite nicely. And also, when you look at the entropy of the contributions, there's a really interesting curve shape. So at about 10 to 15 tokens, the entropy is increased, which means it has increasingly less idea about where to point to in the source. But it's kind of fascinating that there'd be this curvy shape, and then the entropy would go down again at 20 and then go up again at the 23rd token. Now, another way to reason about this is, rather than using the reference prefixes, so the reference translations, why not use the beam search translations? Because they're more regular and they're kind of surprising the model less, because you're putting the model in a comfortable place, so to speak. So she asserts that beam search translations are usually simpler than references. And indeed, when she compares them using the beam search prefixes, the model is more confident about the source, so it's hallucinating less as time goes on. It's the same thing on the entropy. So on the beam search, the entropy is lower, which means it's more confident about the source. So she hypothesizes that the simpler prefixes are more convenient for the model. Yeah, so one way of visualizing this is a bit like tributaries or little rivers, right? So if you give a model something that's inside a tributary, so inside something that it knows about, then it'll just immediately run with it. And in this case, a tributary means it actually understands some relationship between your source and prefix. If you give a model something, let's say outside of the manifold or outside of the tributary, then the model no longer understands what to do. So it'll just start hallucinating and it will just predict something that's grammatically correct because it can't really make any relationship between what you've given it and the source. Another thing she tries doing is just putting completely random prefixes in there. And as you might imagine, the model starts hallucinating quicker because it's just got no idea what you're talking about. It doesn't fit any frame of reference that the model has. So anyway, I really recommend you check out this article. It's beautiful. Finally, she asserts that the training process is non-monotonic with several distinct stages. So when she plots this over time, especially looking at the relation, of the source contributions to the prefix attention, it immediately goes down and then it goes up again, and then it seems to converge after about 20 or 30,000 training batches, which is really interesting, and perhaps you wouldn't have expected that to happen. So the second article on Lena's website is this Information-Theoretic Probing with MDL. What's MDL? It's the minimum description length. Everyone these days is talking about the minimum description length, whether it's Francois Chollet in his Measure of Intelligence paper, or actually it's quite funny. Every time you meet an academic with a Russian accent, they will use the word Kolmogorov complexity. Like every fifth word is like Kolmogorov complexity. I had a PhD supervisor who was like, "Oh yes, I was just going outside for a walk down the road earlier, and I was looking at the sky and considering the Kolmogorov complexity." Anyway, so it comes up everywhere. It's basically the minimum description length for anything. So it comes up a lot in compression as well and information theory. But anyway, Lena says that probing, what does probing mean? Probing means measuring, so like an accuracy would be a probe. Probing classifiers often fails to adequately reflect differences in representations and how they can show different results depending on the hyperparameter. So a lot of this is about accuracy isn't a very stable method, right? So she proposes an information-theoretic probing which measures this minimum description length of the labels given the representations. And the really cool thing here is that rather than just showing the final quality of the probe, so the accuracy, for example, this MDL also shows how hard it was to achieve that particular representation, and it's more stable. So how do we understand if a model captures a specific linguistic property? So in what we do now is we have data, we have representations, and we have labels, and we are measuring to what extent do the representations capture the labels. Now, standard probing is we just use the accuracy, but we know that the accuracy of a classifier is used to measure how well these representations encode the property. Looks reasonable and simple, right? Wrong. Okay, so she says that while simple probes are very popular, several sanity checks have showed that differences in accuracies fail to reflect the differences in the representations, right? So Houston, we've got a problem. The accuracy of a probe is not always reflecting what we want it to reflect. So she introduces this information-theoretic viewpoint. Okay, so what we're getting to here, the TLDR of this article, is that regularity in representations with respect to labels can be exploited to compress the data, right? So machine learning and compression, they are basically the same thing. When we were talking to Sarah Hooker, she was telling us about this, that the reason why the lottery ticket hypothesis works, you can prune 90% of the connections in a neural network and it still works. Sometimes it works even better than it did with all of the ones in there. So what's happening with all of those neurons, right? So they are learning all of the challenging or low frequency attributes, all of the examples that are sitting very close to the decision boundary or, ambiguous between two classes. We're wasting most of the representational capacity, right? So clearly, if we had a lot of regularity in our data, then we would need fewer parameters to encode it. So she has quite an interesting kind of way to represent this. So we've got Alice and Bob, and let's imagine that Alice has all of the data and the labels from the dataset, and Bob only has the representations, and Alice wants to communicate the labels to Bob. So transmitting the data is a lot of work, right? So surely Alice has got a better way to do this, which is compressing the data. So the formal task here is to encode the labels knowing the representations in an optimal way. So essentially what we're getting into here is the cross entropy between the labels and the representations that is the data code length, right? And so learning is compression, and the amount of effort is related to the strength of regularity in the data. So if there is strong regularity, then the data can be expressed with very few examples, and vice versa. So what we're getting into here is variational methods. And by the way, when we interviewed Carl Friston the other week, we were, when I was doing my background research, I was learning all about variational methods and inferences optimization, and of course the KL divergence and so on. And all of this stuff's really interesting. We didn't properly get into it on the episode. So if you folks are interested in us doing an episode on that, then more than happy. I know Keith would love to do a show on that. But this is quite interesting, actually. So Lena's got a section in the article that says, I hereby confirm that I'm not afraid of scary formulas. Wonderful. So you have to explicitly say that you want to see it. But all of this should be familiar to you if you've studied variational methods and the KL divergence. So the TLDR is that the MDL methods are stable and the accuracy is not. So the MDL is a much better measure of probing for machine learning models, because it characterizes not only the probe quality, but how difficult it was to achieve it, the representation. Right, now finally, the other article that we talk about today is this evolution of representations in the transformer. She says we look at the evolution of representations of individual tokens and transformers trained with different training objectives. So translation, language modeling like GPT-3, masked language modeling like BERT, so a denoising autoencoder. And she looks at it from the information bottleneck perspective, right? So she shows that language models gradually forget the past when forming predictions about the future. BERT-style models, the evolution proceeds in two stages of context encoding and token reconstruction, and machine translation representations get refined with context, but less processing is happening. She says, instead of measuring the quality of the representations obtained from a model on some auxiliary task, we characterize how the learning objective determines the information flow in the model. So she looks at how the representations of the individual tokens in a transformer evolve between the layers under different learning objectives. And essentially, she uses the information bottleneck perspective to do this, but that's just a clever way of saying she's looking at the mutual information. So what are the three main tasks in these NLP models? So the first one is machine translation. So given a source and a target sentence, predict words in the target sentence word by word. The language modeling, and you'll know this from GPT-3, of course, so that just estimates the probability of a word given the previous word in a sentence. And masked language modeling, which is the BERT-style model, that's essentially trying to fill in the gaps. So you mask out a word in the input sentence, and then it will tell you what that word was. Right, so we're interested in how the representations evolve between the layers in these transformers architectures, but how does it change depending on the task, right? So all three of the models start out with the same representations of the tokens or the subwords that go in, and they also have the identity and position. But the way that the information flows across the layers is different depending on the objective, and that's the main interest here. So her hypothesis is that these token representations undergo changes layer from layer, and the interactions and relationships between the tokens change, and the type of information which gets lost and acquired also changes as you progress through these transformers models. So the TLDR here on this information bottleneck is that the evolution is in squeezing irrelevant information about the input while preserving relevant information. Now, if we click on this information bottleneck paper, I mean, what have we got here? So that is, we squeeze the information that X provides about Y through a bottleneck formed by a limited set of code words, X. This constrained optimization problem can be seen as a generalization of rate distortion theory. Fucking hell, it's getting a bit heavy going, isn't it? Right, let's come back to where we were. Now, the problem is we only have the representations of the individual tokens, not the entire input. But we can view every model as learning a function from input X to output Y. Now, the first approach that she uses here is computing the mutual information with the input, so the mutual representation of the representation for the successive layers with the input, with what went in. And what she shows here is absolutely fascinating, right? So depending on the training task, for example, BERT-style models, these denoising autoencoders, the masked language model, they actually maintain a fairly high mutual information with the input, even as you go through the successive layers. But machine translation and language modeling, they progressively forget about the input. So if they're forgetting about the input, then what is happening, right? So what she does then is she looks at the mutual information with both what goes in and what goes out. And as you can see, there's a commensurate increase in the mutual information with the output as we go through the successive layers. But the pattern of that commensurate increase changes depending on the training objective. So with master language modeling, it looks like a kind of sigmoidal pattern, whereas with language modeling, it looks like a kind of quadratic curve. So it's very interesting. So she talks about some tricks she uses to estimate the mutual information in this setting because it's quite challenging. She had to use an approximation. But if we get to the rub here, right? The rub is that master language modeling preserves the token identity more than anything else. So when you look at just the token identity through the different layers of the transformer, on master language modeling, it's significantly preserved. She's got a great illustration of this concept, actually. So she gathered representations of tokens, is, are, were, was from lots of different sentences and visualized their dichotomy projections. So the x-axis here are different layers in the model. And what's fascinating here is that the master language model, so the BERT type model, actually preserved the individual tokens throughout the successive layers in the transformers model significantly more than the language model and the machine translation. The other thing is that machine translation best preserves the token position. So she took a large number of representations of the same token for different tokens. For each occurrence, let's look at the position or the top k neighbors and evaluate the average position distance. And again, when we look at a dichotomy visualization here, you can see that machine translation significantly preserves the position of the token compared to language modeling and master language modeling. Okay, so she concludes by saying that with the language modeling objective, as you go from the bottom to the top layers, the information about the past gets lost and predictions about the future get formed. For BERT-type models, the representations initially acquire information about the context around the token, partially forgetting the token identity and producing a more generalized token representation. The token identity then gets recreated in the top layer. For machine translation, though, representations get refined of context and less processing is happening, and most information about the word type does not get lost. This is absolutely fascinating. This reminds me a little bit of our conversation with Simon Kornblith a few weeks ago, because he had a paper which was all about the evolution of representations through, let's say a convolutional neural network with different loss functions. So it's still the same task essentially, but it's different loss functions. And he demonstrated that actually the representations are pretty much the same apart from the penultimate layers, or, the last sort of 20% of the layers, there was a divergence. But of course here there's significantly more divergence because the training tasks are significantly more divergent, I would say. So any kind of approach like this to reason about the evolution of representations and the behavior of neural networks, I think it's absolutely fascinating, and I'm going to really look forward to discussing this with Lena today. Okay, now the most important thing that Lena has got on her website, other than her papers and blogs and so on, is the NLP course. It says NLP course for you in the top right hand corner. You folks must check this out. Sebastian Ruder actually featured this recently on his newsletter, and Sebastian Ruder pretty much is the god of the NLP world, in case you folks didn't know. So in this course, again, in characteristic style for Lena, she has formulated everything beautifully. She's used a lot of graphics and a lot of really cool layout techniques. So she has the concept of lecture blogs, seminars and homeworks, research thinking, related papers, and lots else besides. So on the left-hand side, you can see the structure. So she's got an entire course on word embeddings. And it's too much for me even to go through, but this is absolutely crazy. So one-hot vectors, distributional semantics, count-based methods, word-to-vec, glove, research thinking, related papers. Yeah, it's absolutely incredible. She's also got a course on text classification. So in here she's got a general view, features and classifier, generative versus discriminative, classic methods, naive Bayes, SVM, neural networks, recurrent networks, convolutional networks, multi-label classification, practical tips, embeddings, data augmentation, analysis and interpretability, research thinking again. She's also got an entire section on language modeling, which is what GPT-3 does. So she starts off with a general framework talking about text probability, n-gram language models, neural language models, generation strategies, so things like top K sampling and coherence and diversity and sampling with temperature, all the stuff we talked about in the GPT-3 video, evaluation, practical tips, analysis and interpretability and research thinking again. And she also has a course on seek-to-seek and attention and transfer learning. As I said, I mean, this is just too much for me to go through now. Honestly, if you want to have a really good introductory course to everything in natural language processing, this is the best that I've seen. This really is the best that I've seen. So please go to Lena's website. It's lena-voita.github.io/NLP_course. And of course, we'll put the link in the description, but this really is incredible. So please do go and check that out.
I will need another cup of tea, so...
I operate roughly 2.5% better on peppermint tea.
Yeah, peppermint tea. Exactly.
Welcome back to the Machine Learning Street Talk YouTube channel and podcast. I'm here today with my two compadres, Sayak, the neural network pruner Pool, and Yannic, Lightspeed Kilcher. Now, today we have an incredible guest. We've got Lena Voita, a PhD student at the University of Edinburgh and the University of Amsterdam. Previously, she was a research scientist at Yandex Research, and she worked closely with the Yandex translation team. She still teaches NLP at the Yandex School of Data Analysis. Now, Lena has created an exciting new NLP course on her website, which is called lena-voita.github.io. We'll link it in the description. She has one of the most well-presented blogs I've ever seen, where she discusses her research in an easily digestible manner. She uses lots of visualizations and animations, which I think really communicate her ideas in an innovative way. So picking up the conversation where we left off, what is hallucination and exposure bias?
Hallucination and exposure bias are paying too much attention to the prefix. Hallucination is when you just ignore the source because you want to produce something that's grammatically correct based on what you've already produced. So it's not necessarily that you made a mistake in translation, it's just that you just start ignoring the input, the source. And you're just continuing what you do because that's... At the beginning of a translation, you have no information, right? All you have is the source. And then you might want to pay a bit of attention. But as you translate, you get more and more already translated tokens. And then the language model part kicks in. And then the model can be like, oh, I know how this sentence is going to finish. I know. I don't even need to consider the other language anymore. I already know. I can fit. Like, this is the people that say, I already know what you're going to ask. And then they answer a question that, but you're going to ask something different. So this hallucination is a bit like this. So as exposure bias is more that the distribution differs between training and inference. So in training, you always input whatever token the gold standard has. So you input the source and then you input the target up to token K, and then you try to predict token K plus 1. But all the K tokens are like perfect. They're from a real good translation. But now at inference, you put in your own tokens, and that looks a lot different. So when you make a mistake, you're all of a sudden in a situation where you've never been before, and then you're not trained for this. So anything can go wrong. So Lena, maybe there seems to be a straightforward fix in that. During training, can't we just also input the tokens of the language model? Is that...
Or maybe even incorporate data augmentation, so to speak.
Yeah, there are different ways to fix exposure bias, to fix to some extent. But yeah, it helps to some extent, but hallucinations still happen, and well, basically. And in one part of the paper we're going to discuss, we do look at it as this connection between exposure bias and hallucinations. So basically what a model is doing if it's trained with different training objectives, and if there's a connection between exposure bias and how frequently a model is hallucinating.
So Lena, you seem to be doing a lot of investigations into how these models work. I see on your blog and your papers, there seem to be a lot of you look into probes and you look into how sources and targets influence the final predictions and so on. Is it a general interest of yours, or how did you go in this direction? Because a lot of people who go into NLP or so on, they want to train the models that do something. They want to train the models that
Yeah, I
produce the
know.
language and beat the WMT benchmarks and so on. Your work seems to focus a lot on explaining the models, which I absolutely love. I think there is not enough research in this direction.
If I have to explain this, maybe it's because from the very beginning of my PhD, I was already working with the Yandex Translate team, and almost instantly I understood that almost all this stuff which is going on in research claiming that they have some improvements, actually they don't, if we're talking about really high resource settings and the people who are really trying to optimize things. And maybe that's why I didn't have much interest in this, because it's not like you have to report something, but the things which really work are quite different. I did manage to get something for Yandex Translate. We did get some improvements, but it was nothing of the kind the research usually does. Yeah, and maybe the other reason is that I don't really feel comfortable yet in machine learning, because it's very practical, it's very experimental, because I come from mathematical background, and there you can feel things, you can be sure you proved something, and now no one is gonna doubt that you got this. But here is it gonna work, is it not gonna work? It sounds reasonable, but it's not working. It doesn't sound reasonable, but it's working for some reason. And yeah, it's really different from the feelings I am used to. So I used to certainty to something which makes me calm. So analysis makes me calm because I get to at least a little bit to understand what's going on. That's the main reason. But it's not what I was supposed to do. I was supposed to do context-aware machine translation, and it was very reasonable. It was a really good plan, and it was something which is both useful for production, because currently they're translating sentences individually, and in context-aware MT, I was trying to use larger segments to translate the current sentence, because there can be some kind of ambiguity. So to translate one sentence, you may need a wider context. And it was a really good research topic. And I do have several papers on context-aware MT, but arranged marriage. Context-aware MT is nice, and I could do that, yes, but I always have a feeling that it was something that was chosen for me, and not really, it wasn't really my choice. And maybe there is something out there which I like more, and there is. So, yeah.
Yeah, I find this fascinating. And not only do you investigate methods to evaluate, you have these papers on evaluating representations in transformers and so on, or evaluating contributions of source and target to NMT, but you even, so there is this notion of probes, and this is a paper that I find interesting, of these probes to evaluate embeddings. And also there, you don't go and say, I'm going to make a new one or so on, but you first say why the current ones don't work, and then you go about make a better one. In this paper, Information-Theoretic Probing with MDL, you explain really well why these probing methods of these NMT models or of these NLP models don't work. Would you care to briefly explain what a probe is and why the classic ones are not really good?
Yeah, of course. And I can also explain why I'm really careful in explaining why they don't work. Because I really did have to do that. When you're trying to analyze models in NLP, in generally, you can have different ways to do that. And you can have different kinds of questions to ask. Because in computer vision is simple, because you have an image of a cat, you have a classifier, it says, oh, okay, there's a cat, and you have an attribution method which shows you some parts of an image which contributed, and this is your explanation. But in NLP, it's not, such kind of methods do not work very well. And in NLP, there's whole different kinds of things you can ask. I'll come to probing, right? Let me just give you a general picture of how I see analysis in NLP. when analyzing an NLP model, you can be interested, for example, in how your inductive biases work or how different model components work. Because when you create some kind of inductive bias, you have an intuition what is supposed to happen, right? So you can look at attention, which is quite popular now. You can look at different attention heads. You can look at neurons, and this can tell you something about how your model works. Also, you can look at model predictions. It's kind of standard thing to do is to look at subject-verb agreement, and lots of papers doing that. Basically, you have a language model and you like look at predictions and you evaluate how good it is at some specific phenomena of language. So if you care about language, you can do that. And probing, it's really fun stuff because here you don't care about predictions. You don't care about what your model is generating. You don't care about your model architecture and model components. You just care about representations. When you're feeding data to a network, it can have some layers, and at each of them you have some kind of vector representation of this data. And you can be interested in which kind of things these vectors encode, right? So you have a sequence of tokens on the input, you have several layers, you have some kind of output, and in probing you're interested which kinds of things these vectors encode. For example, do they encode part of speech tags? Do they encode dependencies? Do they encode, I don't know, reference, so such kind of stuff. And what you do is you take some labeled data. For example, you have some data set where you already know part of speech tags. You feed this data to a network, you get representations, and you train a classifier, probing classifier or probe to predict this part of speech tags from representations. And usually you say that okay, if the accuracy is high, probably these representations encode the thing I want them to encode. If the accuracy is not so high, probably they don't encode these things. And for me, the first paper with probing I saw, it was a 2017 ACL paper, What Do NMT Models Learn About Morphology, something like that, by Jonathan Belinkov and co-authors. And I was so excited about it. It was like the first analysis paper I've ever read. And for me, it was like, yay, great. Actually, we can ask these kinds of questions. We can actually be interested what's going on inside the network other than just getting a higher blue score. Because, I was at Yannic, I was at machine translation team. They were all interested in higher blue score. And this kind of things was cool. But then what happened is then that most of analysis started to do this kind of probing stuff. There appeared these models like Elmer, BERT, and all these guys, and there were a lot of papers just measuring different kinds of stuff and making some kind of conclusions. Like, okay, Elmer layer 1 encodes part of speech tags with accuracy like 96.3, and BERT's layer number 6 encodes with accuracy like 96.4. BERT encodes part of speech labels better. And it's not really, it's the whole other question, why do we trust probing? What kind of conclusions can we make out of them? Do we expect these models to be better just because they encode linguistic phenomena? I don't think we're going to answer that kinds of questions, but maybe we could talk about why probing, standard probing doesn't work and what can we do about it.
There does seem to be an obsession with accuracy. And it's such a reductionist number. It's the same thing. Traders have used these Greek letters. What they've done is they've kind of featurized market conditions and they've reduced them down to these single numbers like alpha. And they're just throwing away so much information. We spoke to Sarah Hooker from the Google Brain team the other week, and she was making this observation as well, that when you compress models, you can preserve headline metrics like accuracy. But actually, it's on the long tail where all sorts of, you could argue it's memorization, that all of the underrepresented classes and information is on the long tail and you're effectively throwing it away.
That's a really good point. So mutual information is only part of the things you want. So in a way, in the ideal world, if you had infinite amount of training data for your probe, you'd get a good estimate of mutual information. So whether these representations actually contain information about something. But the fact it's not what you want. Because, for example, if we take a randomly initialized model and just encode things with a randomly initialized model, you're going to get very high accuracy. And very often you cannot even, according to accuracy, you cannot distinguish between trained model or randomly initialized one. And this is a problem with accuracy and with mutual information also, because even randomly initialized models, they contain this information about part of speech text because they know the whole sentence, right? They have this information. But the difference is that usually we want to know if the model encodes something, and it is different. Whether it contains information about something, and you can extract it if you put a lot of effort to it, or it does so by itself. Like it already codes the information, and you can just easily take it. And this is the difference. And another example of why standard probe don't work, it was at NLP last year by John Hewitt and Percy Lane. They developed these control tasks. Basically, they just used random labels. So, for example, instead of part of speech tags, you just assign each word a random label sampled from the empirical distribution of tags. It means that you still have, if you just look at the text, you still have the same distribution, but for different words, they are assigned randomly. So you basically assign that a cat is the preposition, a set is a noun, some such kind of things. And if you train a probe and classify on that, just trying to predict not part of speech tags, but these random labels, you can do that very well. And you're not going to see a huge difference in accuracy. So basically, accuracy can say that your representations encode some random labels, and this is crazy. Because they do contain information about labels, but they don't encode this. And this is what we try to measure.
Yeah, I think a similar kind of observation was made by Sami Vengio's team as well. The classic paper, Understanding Deep Learning Rethinking Generalization or something like that. They also made the statement that neural networks can fit random labels quite easily. And I think you are also asserting something very similar. And I also believe that because Naftali Tishbe's work also lays out the formation from a very hardcore information theoretic perspective, where you start to fit things, and then later on in the training when you start to forget things, and eventually when you start fitting your neural networks with random labels and stuff, there's nothing to forget and there's nothing to fit in the first place. So I think that statement holds perfectly fine. So yeah,
one way of conceptualizing it is maybe saying that if I simply input my sentence into one of these models, and let's say the models, they don't shrink like a CNN, but they just keep layer by layer. Except if they forget something, it's probably always possible to extract whatever information you want. As you say, if you put in a lot of work, it's not the same thing as saying this model pays special attention to part of speech tags. It simply says, look, I can reverse engineer my way to these part of speech tags, and it says nothing about whether or not they are important. And your paper produces or suggests a solution for this, where you exactly hit on this notion. How hard is it to extract this information? Would you care to explain that a bit?
Yeah, maybe let's start with an example. The problem is with accuracy, you don't know whether these representations encode something or you just learned to extract this, put in a lot of effort. And how can we distinguish between these two things? And to understand what is the difference, let me give you an example of a model where we cannot possibly deny that it's a model that encodes something. Let's recall this sentiment neuron paper. So this OpenAI sentiment neuron, right? So OpenAI guys trained a language model on Amazon reviews. So they trained a language model on lots of reviews, and they found a neuron which was responsible for sentiment. So unsupervised sentiment neuron. And so in this case, we cannot I hope that no one can deny that a model encodes sentiment. We have these neurons which is responsible for this concept. And we cannot possibly say that, oh no, it's just a probing classifier extracted this. No, it's a model that encodes sentiment. And to distinguish between the cases where we just can predict sentiment and the model which encodes sentiment, for example. So what is the difference between these two kinds of representations? So if we look at these representations which come from sentiment neuron model, first of all, it would be enough to train a very simple classifier to predict these labels. Very simple. It would be enough to train a linear classifier, and we need only one weight for it, and everything else is zeros. And you cannot do that for a random initialized model, for example. And on the other hand, the other way of looking at this is that to predict sentiment from this sentiment neuron representations, you would need only a few examples, right? Because it's really easy using this one neuron to predict sentiment. You'll need 10 examples and you are done, basically. Mm-hmm. And this is the difference between cases when a model encodes something or you can extract it doing something. So this is an intuition, and this was our example when we thought about how to explain this difference, how to measure this difference. And luckily, there exists this minimum description length framework, this notion. And surprisingly, the practical ways of evaluate this description length, I explain it in more detail. The practical ways of length is basically by looking at the model complexity, how complex should be your model to extract this information, or how hard it is to predict labels using small amounts of data. So basically, the intuition transfers perfectly to these two ways of evaluating description length.
You say it is not only important how well we can predict, let's say, sentiment from a given representation, but also, and you start off by saying how much work we need to put into it, but it's difficult to quantify. And then you go into, let's look at the minimum description length of our model. But then that also is in practice, all our probing classifiers are just going to be linear classifiers of the same size. But then the clever thing I find is to say, but I can count the number of examples I need to train that classifier. So if I count the number of examples to train it, then that gives me a real number that tells me how hard is it to get this stuff out of a representation. That's pretty cool.
It doesn't give you a number of examples. It's just you can look at this amount of effort. So when you have accuracy, you just have this. You have the answer to the question: can we extract this information? But with description length, you have these two parts. So one is this final quality part, which corresponds to accuracy, and basically it's saying the same thing, whether there is this kind of information in the presentations. And the other one, the amount of effort. So in the code length, you can just say, okay, this part of the code says if this information is present, this part says how hard it is to extract it, and altogether is the thing we ideally want to measure.
That's pretty cool. And with respect to these probes, what people want to do in these probes is, as you say, they want to look and they say, this layer does this, and this layer does this, and this layer does this. And this is, in general, is a very fascinating topic. And I think there are as many opinions as there are researchers in the field. It's like I've read a bunch of these papers, and everyone seems to say a lot of different things. You do have an interesting paper on the evolution of representations in the transformer, and where you combine a lot of the similar topics like mutual information and so on as you go through the layers, and you find something very interesting with respect to masked language modeling. What do you find in this paper?
Oh, yeah, it was a really fun paper, actually. It's also ended up having information theory in it. It's the main story. Usually, we talked about probing. There are lots of papers doing probing, just measuring different kinds of stuff, showing the graphs and usually that's it, making some hypotheses, maybe some reasonable statements, but so far it's not clear what is the process which defines this behavior. And in evolution, is what we try to do is to say that there is a logical explanation to all this. Okay, there's a general process which is going on in your network, and it's defined by your training objectives, and everything you're gonna see is gonna be in accordance to this general process. To cut a long story short, in a network, maybe let's start this way. So,
in this paper, you're characterizing how the learning objective determines the information flow in the model, right?
Yeah.
And you're looking at the representations of individual tokens in the transformer and how they evolve in different layers under the different objectives. And you introduce this concept of the information bottleneck.
So, yeah, okay. The information bottleneck, it's a really old method, and originally it was aimed to build a compressed representation of input which contains as much as possible information about output. And it was a goal of information bottleneck. So there are two objectives laid out with mutual information, and the objective is minimizing mutual information with input while maximizing mutual information about output. And in this process, depending on this weights of the objectives, you can get different trade-offs between compression and prediction. So this compression prediction trade-off, how much you forget about input and how well you still can predict output.
Right. You point out that there are regularities in data, and that's one of the reasons why it is compressible. And you're saying that in this process of evolution throughout the layers, you're squeezing irrelevant information while preserving relevant information. But because you spoke about this paper from OpenAI with the sentiment, how does the model know if it's an unsupervised pre-training objective? How did it know that sentiment was salient and that should be preserved?
I think it was preserved because it was important for language modeling objective, because what they trained on were the Amazon reviews. So they were all either positive or negative, and maybe it was easier for a model to decide the sentiment and then just to generate everything rest, like keeping in mind this idea of sentiment.
But do you think there should be a one-to-one mapping between something which is quite anthropocentric? For example, adversarial examples, neural networks learn features that we don't even recognize or care about. So is it just a happy coincidence that it's learned sentiment, which is something that we recognize as a concept?
Yes and no. Yes, because every time you think that a model is doing something reasonable and you're happy about it, and you're ready to say something like, "Oh, look, the model understands these kinds of things," it's not. It doesn't, right? But on the other hand, yes, if there are some things which are important for your objective, it tries to put effort to preserve this information. And yes, sometimes it happens to be something we humans think is important, like sentiment or syntactic dependencies or something like that. So information bottleneck, it's a really old theory, and only recently in 2015 it was shown that if we look at evolution of the layers, so we have input, we have output, we have a sequence of layers, we can think about it as going through this compression prediction stages. So what's going on in the network as you go from bottom to top, and from input to output is you forget information about input and preserve relevant information to output. And the authors of the information bottleneck paper showed that you can think about it, about these layers as going through this information bottleneck procedure. So in a way, your output defines the kinds of information which your network forgets about input. So you have input, but depending on the output, you're going to forget different things. You're going to preserve different things, right, about this input. But it's a very simple story, because it's when we're talking about like the whole network, the whole input and the whole output. When we're dealing with language models and when we're looking at the individual tokens, it's a bit more complicated, because how transformers work, right? So we have our individual tokens, we have positions. At each stage, these tokens interact with each other, exchange information. And at each step, each token has a new representation. a new representation. For example, I was born today, I saw nothing. I talked to you guys. So today I'm going to have a new representation of me because we communicated. I know something more about myself, about the world. I understand myself better in this context and this kind of stuff. And that's what these tokens do. And when we are looking at these individual tokens, we cannot just say about this the whole input, the whole output, because the whole input is your sentence and you're predicting something else. And when we are looking at individual tokens, so your input is current token and its position, and depending on the output for this particular token, its output can be very different. For example, for left or right language model, your output is a next token. So if we look just at representations at this position, they start from the current token and end up predicting the next token. And we would say, okay, it's losing information about input, trying to predict information about output, but that's not everything that's going on, because here I have, for example, I am current token, I have my goal, I need to grow up and become this next token. But I also have these other guys around me, and they also have to grow up and become this next token, whoever is the next token for them. And I need their help to help me grow up and become this next token. And these other guys also need my help to predict whatever they want to predict. And this is when our story is different from the standard bottleneck setting, because in standard setting you have the whole input, the whole output, and that's everything. But here we still have input, for example, current token, we still have output, but we also have to preserve some information which needed for other tokens. So I cannot forget everything about myself, because I need to keep this information because other guys need it. And this is when it gets interesting. And if we look, for example, at these objectives, well, the left-to-right language model is quite simple. We start from the current token, we get the next token in the end, and in this process, we can forget something about the current token. Something is still preserved, but if in the end I need to build a representation of some other token, I need to forget about myself, right? It's no longer about myself, it's about what comes next, what comes after me. But if we're talking about mask language modeling, it's very different, because so how this MLM model is trained. So basically it's BERT training objective. It's the main part of the BERT training. You start from some kind of token. It may be a mask token most of the time, right? It may be a random token, or some part of the time it may be even a real token. And you have to go out there in the world, communicate with others, understand if you're a mask, that you have to understand who you are. If you're a random token, you have to figure out somehow that, okay, I'm random. I need to somehow to get to my true self. And if you are a correct token, you still have to understand somehow, okay, I'm in my place, everything is right. I just need to keep myself untouched and go straight to the finish line. And this is a tricky part, because on the one hand, these tokens have to go out there and communicate with others to figure this out, right? This has to happen at some point, this what they were trained. But after that, they have to fulfill their goal to predict token identity in the end. And so if you look at the training process, so in training, almost most of the time, your input and your output are different tokens. So on the input side, you have either mask of some random token. On the output, you have something which has to be there. And if you look at this training setting, it's forgetting information about input, which is irrelevant, and building information about output. So in training, everything is simple, because it's very similar to left-to-right language model when you have one token on the input, some other token on the output. But if you take an already trained model, what you have is that you start with real tokens, they communicate, they build some contextual representation, some generalized representation of this context. And as you go up to the highest layers, you start losing this contextual information and building a representation about token again. So it goes in two stages. So first, it's context encoding, where each token forgets a little bit about itself and builds a contextual representation, elastic representations of the things which could be in this place. And then it's token reconstruction. It's where you forget contextual information and try to reconstruct this token. And that's why when we are looking at a lot of papers doing probing tasks, they say something like, okay, let's try to predict, for example, part of speech of the current token using representations from different layers, for example, for different models. So what you're going to see is, for example, for machine translation encoder, it just goes up because you're encoding, right? The decoding part is out there. You don't see it here. When you see a left-to-right language model, it goes like up then down. Okay, and it is reasonable because language model has to build representation of next token. It doesn't care anymore about part of speech text of the current one. It cares about the next one, and that's what we show. And for math language modeling, there's also this pattern, but for different reasons, as we see, right? You also first you build contextual representation, and then you forget it. And in different papers, doing probing, doing different kinds of probing, doing other stuff, for example, even if you look at the BERTScore paper, in the appendix, they have this graph showing how effective is this BERTScore depending on the layer they're taking representations from. So a couple of words about BERTScore. So the idea is to build an evaluation metric based on semantics, and for this we use representations coming from BERT because they encode meaning in contrast to BlueScore, which encodes just n-gram overlap. And in the end, they have this graph showing when using BERTScore, you can take representations from different layers. And they evaluate how effective this metric is depending on where you taken these representations. And what they see is, again, it goes up then down because top layers are not about context anymore. They're about reconstructing this token, and they forget this contextual information. And also this BERT Rediscovers classical NLP pipeline, and so on and so forth. I could talk about this forever because basically all these papers are showing the same pattern. They are following, basically all the results are following this general process. And it is all explained by this old concept of information bottleneck. And I think it's cool. At least for me, it makes sense finally. Finally, something makes sense.
So in one of the figures that you have included in the blog post where we see how the mutual information plateaus for a bit in deeper in the layers, and then it starts to again increase for mask language modeling. So would you attribute BERT's bidirectionality to that? Because you also mentioned that a single token's representation is also contributed by the other representation.
Not really. I think it is important that it has access to all context and not just to left context like left-to-right language model. But it's not only about bidirectionality, it's about a chain objective. Because, for example, a machine translation encoder, it's also bidirectional because it has access to all context, right, at the same time. So this is about this evolution. It's about losing information about input and accumulating information about output. And if you want the purpose, so imagine these tokens born blank in this word. So their word is a sentence or a text. They are born just being a token identity with their position, and they are born to become something in the end. So they already have a goal, and what they do in the sentence, what they do in this text, how they interact with each other, which information they take from each other, is defined by this final objective. Sometimes I wish we had one because it would make things much easier. just imagine, you would know what do you have to do, what to take from people, how to communicate them, and basically all your interactions are defined by this final goal. And unfortunately, differently from language models, we don't have one.
So this in turn kind of depends on the difficulty of the training objective to some extent. So maybe it would further allow us to quantify how difficult is a training objective really is based on the kind of hypothesis that you have made in the paper. So yeah, really interesting.
Yeah, so it's really good point because yes, roughly speaking, your target objective defines the kinds of information you lose about input. right? And the more complicated your target objective, the less things you want to lose, maybe more things you have to encode. So yeah, of course, maybe it could be used, the amount of information you lose about input, maybe it could be used as a measure of how complicated your training objective is.
Yeah, definitely. And in all of the training objectives that you have experimented, clearly mask language modeling is a winner because of the two qualities it gives us as a byproduct. For example, context encoding and label reconstruction. None of the other training objectives allow us to do that at this point. Yeah.
Do you think there is how influential is the data set in all of this? Because you've said, for example, in these Amazon reviews, there was a clear neuron, maybe this is an extreme example, but a neuron for sentiment. And presumably, and you've said so, is because probably these Amazon reviews, they are either good or bad. So that's a very strong signal. Presumably, if we only had good reviews, the model would, even with the best objective, would never learn to encode sentiment because it doesn't need to. So how much, do you have any ideas of, or how important is the data set, or what do we need to do when we collect data sets?
Oh, it's a hard question. In generally, about our analysis, we controlled for the data set just to exclude influenced data sets. So we use the same data, just like the same everything, the same random seeds, just different training objectives. But yeah, of course, depending on training set, the things which a model finds useful for the training objectives are going to be different. And there's a whole different story of how to create training data set, and it's a huge problem in machine translation also. And there are lots of kinds of adversarial examples, and we know that in SNLI tasks, for example, the models rely on some triggers and not on semantic things, but on some easily, maybe even on some triggers which are not really relevant to the task. And I don't think I'm going to have a very good answer to that because, it really depends on the task.
Maybe there's a little bit of a bigger question in that, after your investigations and so on, what is something that you think most of the community still has a wrong idea about the language models or translation or whatever you looked into? What is something where you feel that most of the community is wrong about?
Yannic, I'm just a PhD student. Imagine me answering that. I'm not going to have future in this field.
This is the place for strong opinions.
Yeah, we welcome.
I'm not going to say that. Okay, the whole community is not doing that. I'm not going to say that. But we clearly have to be honest with ourselves about the results we see in the models and how we interpret them, because it's really important. For example, it's important if we're talking about the evolution paper, the main outcome, maybe we need to understand the general process behind this phenomenon rather than measuring a lot of stuff. Because once you understand this general process, you don't need to measure the stuff and say, the patterns are different. We don't know why it is, but we observe that they are. Of course they are. They have to be different. It's supposed to be so. It was their destiny to behave this way. There was no other way it could be done. But I think that was my point from the evolution paper. And will this description lengthening? Yes, it's important to understand what's going on. It's important how to measure it. But it's really a hard question of... maybe the main thing we need to work on is how to interpret the results. We have lots of methods, so we can measure different stuff. We have lots of this test sets for probing classifiers. We have a lot of benchmarks, but so far I think we don't know what to take out of these results. What does it mean that this model gives you 0.3 accuracy better on some benchmark? And
I don't want to go too far down this path because it goes on forever, but we've been speaking to some good old-fashioned AI people, and they have been telling us that natural language processing is not the same thing as natural language understanding. And statistical language models, as we can get into a philosophical debate of what does it mean to understand, but if we ask GPT-3 something like how many feet fit in a shoe or anything that requires what you might call reasoning, it doesn't seem to work. So do you agree that natural language processing is glorified statistical text processing, or do you think we can actually make something that understands whatever that means?
Well, it's called processing. Of course it's processing.
Okay, that's a simple answer.
So yes, of course, I don't think the model understand, because they don't understand things as we do. And at the very least, you need to, if you work at least a little bit in this field, you'll see what actually your models are doing. You'll see that it's just some kind of statistical behavior. So there are some statistics in the data, they capture the statistics and they get it out for you. And they're not going to understand things as we do. And maybe an example from context of AMT, it's how I usually illustrate what's going on in context of AMT and why do we need context. For example, imagine you have a sentence, I'm here telling you this. And without context, it's not possible to understand who is I, where is here, who is you, and what is this that I'm telling you. And even with context, it wouldn't be possible to understand just from the text what's going on. You have to be part of it. And maybe we'll get better. Yeah. So there's a whole other stuff, there's grounding, other modalities coming in play, and so on and so forth. And I think at least when we are dealing only with text, it's not possible to really understand things. And even if with these language models being as good as they are, if you play with them, you still see that it's just capturing some statistics. It's not really understanding. It doesn't have this underlying meaning behind it.
Because when you talk about context as well, I think by that you might also mean knowledge or common knowledge. And this guy was pointing out that there's lots of missing information in our communication, and we have a common knowledge, so we, in a way, we compress our communication, and then you need to perform some reasoning to fill in the missing gaps.
Yeah, but to that end, one could argue that an entire our models, lifetimes are entirely limited to the training data it's exposed to. But we as human beings, we are exposed to all the other things that we get to see on a day-to-day basis. So the sense of common sense would, of course, be far more elegant capacity for us, because we are entitled and exposed to a whole lot of things, whereas a model is only exposed to its lifetime of interacting with the training data set. So there are all kinds of arguments to that line.
It does raise the question, though, of what does it mean to understand? And I think where these GOFAI people, they say that there's lots of lexical ambiguities in language, but with natural language understanding, you're trying to get to what was the thought behind an utterance. And there's no ambiguity there. We always seem to understand what we mean. But I don't know how to verbalize that, because just as an example, we've been talking to GPT-3 quite a lot. We've managed to get access to it. And it's really difficult to ascertain whether or not, if I was evaluating it, if I was doing some pronoun disambiguation or something, it's really difficult for me to evaluate whether or not it has actually got the right answer. Because it's just given me a bunch of tokens and it might contradict itself.
It's too smart for you.
Probably.
It's too smart for all of us. It's just tricking us. I'm just a stupid statistical model. And it's just manipulating you to take over the world. But it's really, and it also raises the question of, I think what people try to say is that even though GPT-3 and these other language models are only trained on their training data, the emerging thing is something like understanding. But I think that's hotly debated, and probably no one has as of yet a real answer.
It's even hard to define what do we mean by meaning, and let alone just to evaluate it somehow in a model.
Exactly. So you, switching topics a little bit, you do have an NLP course.
I do, yes. Well, it's NLP course. It's called NLP course. It's not full yet. It's something I was working on my isolation this summer while I was waiting to get a UK visa, because it's a long story. But yeah, I left Yannic. I was supposed to come to Edinburgh in the spring, and yeah, I had everything planned. I had my suitcase packed, and now the quarantine happened, and yay, I got stuck for 6 months in Moscow for no reason, with no plans to have an apartment there. So yeah, and this is when I created this NLP course. And this is, guys, if you're stuck in 4 walls, no communication, this is what came out of me. Maybe you can, at some point, you can share what came out of you, but this was I did. So it was my attempt to come up with something useful when I didn't know what was gonna be like, what teaching was gonna be like in autumn, because I teach an NLP course at this Yandex School of Data Analysis, and I was planning to move to Edinburgh in spring, then came back to Moscow to teach, and then come back. And with all this quarantine, I wasn't even sure that we were going to have the course or teaching or all the stuff. And yeah, that's what got me thinking about it. And there were other questions about teaching per se. I thought about a lot in previous years, because I had a feeling that the standard format is not suitable for everyone. It doesn't have this individual approach I would love to have for my students, because you have a lecture. Yes, you have to tell something people, right? And on the one hand, some people came there just to part the course. It's reality, because I don't think NLP is the best thing everyone should be interested in. We have our own interest, right? And so for some people, it may be too much. For other people, it may be too little. Some people just want to know what's it about. Other people just, they really want to do research afterwards, and they are ready to put effort to read papers, to all this kinds of stuff. So it's about the lecture part. And the other question is, okay, we have a lecture, and what is the best way for students to just, recap some material? It's not feasible just to click through the video or look at the slides, because it's not user friendly, and the other thing, again, it's about usually, yes, you can have a lecture, you can give some links. Okay, read also these papers, right? And a bunch of papers. And when you're starting, it's nearly impossible to read all of them, to understand perfectly, to get the idea, to understand how the field is going on, because, papers by themselves, they are not usually user-friendly, and we talked about this meaning, common sense, and all the stuff. It's when you're coming into the field, when you're trying to read a research paper, to understand it perfectly, you still need to have some kind of understanding of this, common knowledge of the field, right? At least to get this understanding. Okay, these parts they write because just they have to, related work introduction, right? And this is the main idea, and this is why it's cool. And it's hard when you're starting. I think it's hard to get this main idea quickly. It's impossible for a young student to just skim through the paper, get the main idea, and move on, and to get this feeling of the field. And and this is my NLP course was my version of how I see it may be done, because it first of all, it's a suitable format for students to recap some material, to look up to the things, because it's like a lecture in the blog post with lots of visualizations, and they can play with things. For example, if there are embeddings, they have this Disney projection. You can basically you can walk through this embedding space and to look what's going on. So I put really a lot of effort to the lectures to make them interactive, to make them, there are a lot of stuff where you have to where I'm saying just like, okay, just go through the slides, and each student, like by themselves, can just go through the slides and at their own pace. Because at lecture, again, it's gonna be too slow for someone, it's gonna be too quickly for other people. It's never gonna be good for anyone, never. But in this format, they have an opportunity to just do it as they like, do it at their own pace, just to take all the time they need to look at the figures, just to look at the interactive stuff in their own speed, right? And this is about lectures. And the other stuff I have is related papers, but it's not just links with papers, it's little summaries. It's also illustrations with all the stuff. And what I try to do is to give the students an opportunity to quickly get a general idea what other things are going on in this field. For example, there's a lecture, basically like word embeddings, the standard stuff. Yes, there's a statistical ones, count-based, neural-based, and all the stuff. But after that, okay, there can be, for example, gender bias. Let's see how this can be mitigated. We can look at semantic shift. We can look at multilingual things. We can look at theoretical explanations of what's going on. We can look at different ways to evaluate them, and so on. And so you have a lot of papers, and it's just enough to like a short, like 2-3 sentence summary, and it will take you about like 10 minutes to go over all the papers and just to get an idea of what are other things which are going on. And you don't need to spend a week reading all these papers, you just need 10 minutes to go over that. And if there is something you like, you can click to expand this thing and just to read the full version of the things you care about. And after that, once you get this main idea, once you understand it, given only the context of the lecture, which is nearly impossible if you read the paper right away. After that, if you're interested enough, you can read the original papers. I'm not against that, don't get me wrong. But once you get this main idea, you are like ready, you're equipped enough to go read the paper, and when keeping this main idea in mind, you are ready to frame all the things you read and this general understanding behind it. And but related papers, it's not my favorite part, and it's not the favorite part by feedback. By the way, I was at NLP last week, and surprisingly, I got a lot of students from different countries contacting me and saying, Lena, we are taking your course, that's great, do it more. And so it was really great. And what they said, they liked more the research thinking exercises. And this
same.
is the part
my
which
favorite
is,
part as well. I was going to come to that. So my personal favorite part from your course is you encourage students to ask research questions, formulate research questions, which is uber cool to me. I am a big MOOC fan, by the way, and I got to know about your course from Sebastian Ruder's newsletter, just as a fun fact for our viewers. So immediately I jumped straight to it, and when I discovered that section on research questions and stuff like that, so I found it to be uber cool, and it's one of my personal favorites of your course as well.
Yeah, so what are these exercises? When I worked at Yandex, it may sound crazy, but I was a grown-up research scientist with grown-up responsibilities, and when I left, I was a senior research scientist, and one of the things I had to do was supervise interns and students. And we did have some papers with my interns and students. And the main, when you're working with students in this way, that it's really hard, even if it's a super cool student, if they learned all the lecture stuff, there's still this point when there's a difference between when you're given information and when you have to do something yourself and do something novel, right? Even think about ways to extend what you learned. So you can, for example, someone comes to you and tells you, here are words embeddings, they work like this, these are their properties, and do something with it. It's what am I supposed to do? How am I supposed to extend it? What could be possible ideas? And this is a really scary point for people because, that feeling that you have no idea what to do, that you have no idea how to do it. And even when you start reading papers, you read the paper and you don't see straight away, well, if you see you're super cool, you're gonna do great in this field. But usually what happens is that when you read a paper, oh God, this is so cool. Some cool guys did some great stuff. How did they come to this? How am I supposed to come to this? And it's really that point when you can get scared and this is the point you can get away. So here my purpose was to give that feeling that it's not just an information, it's not just something static you are given and that's it. It's just enough to be reasonable, to try reasonable things, and they work. If they're not working, you just try another reasonable things. At some point, it's going to be okay. So, what is the research thinking exercise? So you have a lecture, and then based on something you already know, I can ask some things. For example, we saw this and this stuff. I think this is good, or what kinds of problems can be there, right? Imagine some kind of example. What do you think about it? And a student has to think, at least for a minute, and they can click on the button to expand the answer, what I think about it, or what other papers thought about it. And in this way, after that I can ask, okay, when we understand the problem, how can you fix this, for example, based on this idea? And so you have some kind of guidance, you have in a way someone asking you questions. And my idea was to replace, since I didn't know if I was going to teach this course in person, my idea was to do everything possible to replace myself and put something out there instead of me. And this was like me asking questions, guiding students through some path of thinking, I don't know. And studies show that when you put in effort to get some kind of information, you are more likely to learn it and not when you're just given some kind of information. And even if you're just read this question, you think about it for a minute and you look at the answer, it's going to be it's very different if I just tell you this. It's very different. And if you're a really good student, if you're listening to this, please do it this way. Just read the question and play that out for a day or two or maybe a week. Even if you're not thinking about it all the time, it's just something is going on in your brain. You'll notice something is going on. And when you come to this...
Because if you think about it, you're creating some kind of a framework in your brain where you have concepts and you can hang things off those. I feel sometimes when I prepare for Street Talk episodes, I have to understand something in order to explain it. And when I do understand it, even if I forget it, I'll very quickly get it back again if I need to, because I understood it at some point in the past.
And because of a need, that understanding part rose from a need, because you had to prepare it for the ML Street Talk episode, and needs give birth to this kind of effectivity to some extent.
It's not just someone told you about this, right? You put your effort to do that, and that's what counts. And if you're willing to spend at least some kind of time to do that, first of all, you'll see that most of the time it's enough, just based on one lecture of the common stuff, you'll see that even reasonable, when you're just being reasonable, it's usually it's already quite a lot. And you'll see that, okay, maybe I'll do this way. And you click and you see, okay, there was a paper which did exactly the same. And it's not, and in the first lecture I also have examples, for example, based on 1995 paper for count-based embeddings, how to make them better, and modern ones. And you'll see that the process of thinking, the research process, is the same. So you have some understanding of what's going on right now, of the current state of things. You are just starting being reasonable and you already get some results. Okay, of course, in the end, you can end up very far from what you started. And in the end, you can get a paper which looks really cool, and you didn't even realize how this happened. At least for me, it's how this happened to me. Okay. But yeah, and I wanted to just help to people to get this feeling that it's okay, it's not that hard. It's okay that you just read the paper, you don't understand how to get this. This is how you can get to know how to get to learn about this process, at least to not just take the knowledge, but to put your effort to expand it. And I think it's going to be useful. I hope it's going to be useful. Yeah, it's not finished yet. It's going to be more papers, more exercises. Yeah.
I was going to ask you, what tools do you use? Do you use cloud providers? Are you a MATLAB hacker? Are you a Python person? Sketch out your tool stack, and what is a day in the life of Lena hacking, doing all of this stuff?
Day in life after I already knew what HTML and CSS is, or before. Because when it started, it was like, okay, I have this huge idea. I don't know how to do what is HTML, how to do all this cool stuff to make it look good. So about 1 month in June, I spent just to trying to understand how HTML works, how CSS works, because I had personal page, but it was like from some template. I just inserted my name and like, this kind of stuff. But the course, it was different things. It was like to design the whole how it would look like. And for me, it's important because it has to give me that feeling I have inside. And if it doesn't, if it's not right. Yeah. So coming back to the course, so it's HTML, CSS, a little bit of JavaScript, but for simple things, just like pushing the button and do something. For pictures, it's, you'd be surprised, it's PowerPoint. It's PowerPoint, print screen, and paint it to GIF. Something like this.
It's amazing what you can do in PowerPoint. For your experiment, when you write your papers and so on.
Yeah, for experiment, it's Python. It's Python, it's TensorFlow, not because I'm a masochist, but because we had to use it at Yandex, because at Yandex I used Yandex internal framework, and it's on TensorFlow, so I use TensorFlow. I'm not very happy about it, but now it's a strange situation because I'm not happy with TensorFlow. I don't have much experience with PyTorch, so I'm stuck on this one, and to be honest, I don't really like coding. It's my bottleneck. It really is my bottleneck. I like reading papers. I like thinking. I like drawing fancy pictures, but I don't like coding. Yeah.
So you're more of a scientist than an engineer.
Yeah. My background was in mathematics, and this was because I didn't have to do anything. And what I liked about mathematics was, at least what I thought how it worked. You don't have to know anything. You can just derive everything you want. With history, with other stuff, even with physics, you have to learn things. You have to learn formulas. You have to learn facts. With mathematics, you don't have to do anything. Maybe I'm just lazy. I don't know. You have to know nothing. You can just derive all the stuff. And it's so beautiful. You come to the first lecture, you have definition of real numbers, right? You have this 24 axioms, and that's it. You don't need anything after that. You can just get it out of it. And yeah.
We'll quote you on that. You know that. We'll just put this clip live. In mathematics, you don't need to know anything. You don't need to do anything. By Lena Voita. Just this clip. It's going to be...
I think it's the do bit. You don't need to do anything.
But it was the way it was for me. And yeah, now when I have to run experiments, because without an experiment, I don't know if it works or not. You don't need to do that in mathematics. You just prove things. You're sure. Everyone is sure. Everyone is happy. You're done. You're good.
Because Python is the complete diametric opposite of that. Because at least with some statically typed languages, you have some idea when you compile it whether it will work or not. Whereas with Python, you're stabbing in the dark, aren't you?
Yeah, true. At some point, I used C++, but it was a funny story. when I interviewed for Yandex for this position at production for the first time, they warned me they're going to be coding interviews. And I was a mathematician before. I never had any kind of coding. I had some kind of coding at the university, but it was like done and forgotten. And for interviews, I actually read first several chapters of Strauss Troop just to understand, okay, this is how C++ works. Okay, with the algorithmic side, it's good because it's like basically solving a mathematical task. You understand the algorithm complexity and that's it. And it's a funny thing that they interviewed. So they have like C++ coding interview, algorithm interview, statistics, probability theory, machine learning for this first position. And apparently then when at some point I needed something from production teams, and that was there was the guy who interviewed me, we were like, oh guys, we are data scientists, we need you to code this and that. They're like, you have Lena. She's so good at C++. You just have to give it to her. Why are you coming to us? And Lena, like, in the stage where I never saw like a real C++ code in my life before that. Yeah, that's the problem with interviews and with code on the desk. As a mathematician, I can do that. I can do like actually open some framework. If you give me a computer and ask just open something in C++ and write, I won't be able to do that.
Amazing. Lena Voita, it's been an absolute honor, and thank you so much for joining us today.
Thank you. It's been fun.
Thank you.
Amazing. Anyway, I really hope you've enjoyed the episode today. As always, we've had so much fun making it. Remember to like, comment, and subscribe. We love reading your comments, and we'll see you back next week.